Hello all, this is the course CE842 Performance Based Seismic Design of Structures. My name is Fawad Najam and I will be resuming this course from where we ended before this COVID-19 situation. So in this course, I will be discussing the finite element modeling for linear elastic analysis of structures. I will start with the fundamental principles of finite element analysis, and then I will take you through all the steps required to complete one linear elastic model of a structure, starting from structural idealization and then the structural discretization, which is the basic principle behind the finite element analysis. I will be introducing all those elements in which you can discretize your structure. I will also be discussing the modeling of structural materials in different finite element software, especially the CSI product ETABS. I will also be discussing the load patterns, load cases and load combinations, and at the end I will be discussing post-processing and getting the results from finite element software, especially from ETABS. Just to start with, I think you might have remembered this figure from the last lecture in which we discussed the code-based design procedures, which are the specified procedures based on empirical expressions, different charts, tables, and some set of rules and limits which are prescribed by building codes. I think with the advent of computing tools and latest technologies, now we can shift from this specified procedures to more explicitly like 2D linear static finite element analysis, which are matrix based methods, or maybe to this full three-dimensional nonlinear inelastic dynamic analysis, or the detailed nonlinear analysis of structures. Just to bring things in perspective, let me explain where we are in this course. We have already discussed lecture 4A, which is based on the code-based seismic analysis procedures. In that lecture, we have discussed three seismic analysis procedures. The first one is the equivalent lateral force procedure. The second one is the response spectrum analysis procedure, and the third one is the linear response history analysis procedure, which is also sometimes referred to as the linear time history analysis procedure, the direct integration procedure, or the linear dynamic procedure. Now is the time that we will discuss what are the computer modeling issues which should be addressed before we can apply these three procedures, and that we will discuss in this lecture 4B, where we will be discussing the linear finite element modeling of structures. Linear means that all of the material properties and the cross-sectional properties and the material properties, they are linear, they follow the fundamental linear relationship between actions and corresponding deformations. And then we will also have a lecture, next lecture on nonlinear seismic analysis procedures, these ones, and then another lecture on the nonlinear modeling of structures, inelastic computer modeling of our structures. So, but now for this lecture we will be discussing the linear elastic modeling, this lecture 4B. Before I discuss any further details, let's have a quick overview of what the finite element analysis is and what are some of the principles on which it is based upon. In linear elastic modeling, we look at our structure essentially like a very big spring, which is governed by a kind of a spring constant or the stiffness of that spring, which is in our case, in real structures case, is the global stiffness matrix of the structure. The force applied to the structure and the corresponding deformations, they are linked with each other through this global stiffness matrix of the structure. So our target in this whole procedure is that the excitations are given, which can be in the form of loads, can be in the form of applied vibrations or settlements or thermal loads, and our target is to calculate the structural response in terms of displacements, strains, stresses, and stress resultants. And by the way, in a finite element formulation. All of these responses are determined exactly in the same order. First we determine displacements and then we convert them into strains, and then those strains are converted to stresses using the constitutive relationships, and then those stresses are summed up into what we call as stress resultants. The governing equation of motion which we use for this linear elastic analysis is the same as the generalized form of Hooke's law for multiple degree of freedom systems. The force vector is linked with the displacement vector through a stiffness matrix of the structure. In the traditional matrix analysis courses, you are already familiar with the K matrix, the global stiffness matrix of the structure for some basic kind of frame elements or beam elements maybe. So why we are doing this analysis, this linear static analysis? Because we want to determine the response of a structure to the applied excitations. And why we want to determine this response? Because ultimate goal is to design our structures. We want to ensure that the structure can sustain the excitation with an acceptable level of response. This procedure is called design, and this procedure in which we determine the response of a structure to given excitation is called analysis. So if you look at the real structures general governing equation of motion without any simplification or idealization or discretization, these governing equilibrium equations, they look like this. They are either in the form of partial differential equations or the ordinary differential equations. For example, in this case, if you are given with a structure which has both body forces and surface tractions, the equilibrium equation would look like this, which simply says that the sum of body forces and the surface tractions, their sum should be equal to 0. That 0 will ensure that the structure as a whole will remain in equilibrium. The direct solution for the mathematical models like this, the exact models I will say, the direct solution for these models are only possible for simple geometry, for simple kind of boundary conditions, and for simple kind of applied loadings. For real cases, for complex geometries, for complex kind of excitations, the exact solution, closed form solution for equilibrium equations like this is not possible. And this is where we need a kind of a rigorous numerical procedure like finite element analysis. Before we apply that, we have to idealize our structure into form of what we call as a structural model in our computer. Structural model is a kind of a compromise between a real structure and its mathematical representation. So you have a real structure on one side, and you have a kind of a mathematical representation of your structure, mathematical representation, and in between is your structural model. So this structural model will comprise of all those assumptions which you will make in order to simplify our real structure so that it can be reasonably described by a mathematical model. That mathematical model should have basically is simple enough to be governed by linear equations, to be governed by matrix algebraic equations, so that the FEM solution can handle those solutions to come up with the final displacement and all those responses which we mentioned earlier. So first things first, why we need computer modeling? Because a real structure with all of its complexities and complexities in applied loading and geometries cannot be analyzed. The direct solution, closed form solution is not possible. It can only be load tested to determine response, which is not a practical case. By the way, for each structure we cannot do that. We can perform a load testing to some specific elements of a structure, and that too can be up to a certain extent, not for the whole structures. What we can do is that we can only analyze the computer model of a structure. So we therefore need tools to model the structure and to analyze the model. Tools can be different software, for example, And the analysis tool, for example, can be FEM. So there are several FEM based analysis tools available which will guide you through whole of the process. I will also explain CSI E-tabs in this lecture. The later part of this lecture will be comprised of the direct hands-on kind of training or demonstration on CSI E-tabs also. So finite element method is a method based on discretization, and the underlying idea is that we can divide our structure into simple elements, and the behavior of those elements can be well understood and described by simple mathematical relationships. So finite element analysis is a discretized solution to a continuum problem using FEM, finite element method, and that method is a numerical procedure for solving partial or ordinary differential equations associated with field problems with an accuracy acceptable to engineers. In our case, the field will be the displacement of our structures. So field is the displacement, and we are required to calculate this displacement against any given excitation or loading for our structure, and we will divide our structure into simple elements which we will call them finite elements. So here in this figure you can see some finite element models of some structure here, and here you can see the finite element models of a human heart. So you can model anything as long as you know the stiffness properties of that object. To give you an example of how the idea of discretization can help us in solving complex problems, let's see how a famous mathematician Archimedes calculated the value of pi using a simple idea of discretizing a circle into a polygon. So let's see if we have a circle here, this one, and we already know that pi is a ratio between the circumference, let's call it capital C, to the diameter of the circle. C is the circumference of this circle. So no matter how big or small circle you have, if you take the circumference of that circle and divide it with the diameter, you will get the number equal to pi. So for the purpose of calculating the circumference of this circle, let's discretize it into a regular polygon with all equal sides. So here we have a polygon and we have its points or nodes here, and we divided it into different sides, for example 1, 2, 2, 3, 3, 4, 4, 5 and so on. As we increase the number of sides in this polygon, the figure will correspond to the actual circle. So for any two nodes I and j, we can write the length of this segment ij as a function of n, such that as the value of n increase, the length of this segment ij decrease. So let's define this length as 2r sine pi by n, and we can see here now that when n increase, the value of sine pi by n will reduce and the segment length ij will also reduce. And for very high value of n, this ij length will reduce to a very small value. So now if we multiply this segment length with the value of total number of segments, we will get the circumference. So we will get this circumference by multiplying n, which is the total number of segments, multiplied with the length of one segment, which is 2r sine pi by n. This is the length of one segment, and we multiply it with the total number of segments n which this polygon has, and then we will get the total circumference of the circle. Basically for very high values of n, this value of c will correspond to the actual circumference of the circle, and the polygon will correspond to the actual circle. So if we divide this circumference with the diameter of the circle, we should be able to get the value of pi. So pi is defined as the circumference divided by the diameter. So now we have n into 2r into sine pi by n divided by diameter. Let's write it as 2r. This 2r and 2r will be cancelled out. So we can write pi as pi equal to n times sine pi by n. For very large values of n, this whole thing should correspond to the value of pi. So here you can see that pi is equal to n times sine pi by n, and for different values of n here, for increasing values of n, you can see what we are getting from n pi sin pi by n. And for very large values of n, like for example 256, we are getting a value which is very close to the real value of pi. This is the exact value of pi up to 16 places, this one. So we are getting a number which is quite close to this number up to some significant figures. So that's how the idea of discretization can be used in simplifying a problem which cannot be solved with exact solution directly. So we can discretize it and solve it up to an accuracy which is acceptable to us. So a brief history of finite element method. It grew out of the aerospace industry. In early years of its development, Boeing took part in its development, and then post World War II, jets, missiles and space flights required the developments in this area because there was a need of lightweight structures which require accurate stress analysis, and also the developments in finite element method are paralleled with the growth of computers. Some early developments in this area: in 1940s, different researchers laid down some fundamental work which later on helped in the development of a detailed version of finite element method. In 1950s and 60s, some of the further concepts, for example energy principle for matrix methods, were formulated by different researchers. More importantly, Raycliffe and his colleagues worked out the mathematical formulation for 2D elements and also coined the term finite elements. In 1980s, with the development of computing tools, there were wide range of applications of finite element analysis, and this method was integrated with computer-aided engineering with two of the most important powerful computing tools, which are automated mesh generation and the graphical display of analysis results and models. In 2000s and onwards, now the finite element method is an integral part of the computer-aided design optimization using finite element analysis, nonlinear finite element analysis, and with better CAD or computer-aided engineering integration. So the finite element analysis is the basic engine of all of these new technologies and all of these new developments. The current applications include almost all of the basic engineering applications, including mechanical, aerospace, civil, automotive engineering, which require structural or stress analysis which can be static or dynamic or can be linear or non-linear. Other applications include fluid flow, heat transfer problems, electromagnetic field problems, soil mechanics, acoustics, biomechanics, and the list continues. Here are some of the examples of finite element models. This is an example of a two-dimensional model of a mechanical assembly. And you can see here these lines. These are basically the boundaries between different finite elements. So for example, this one, this triangular finite element you can see, and here another example of finite element, this one, and then some other elements, these ones. So you can see here that this mechanical assembly is comprised of different elements, and the colors on this model show their values of stresses against any applied loading. Here is an example of a three-dimensional model of a mechanical assembly. Here again you can see that it is made up of different elements, and the colors on this model show the values of stresses. Here again you can see that this is a mechanical assembly, and the model shows different colors based on any given applied excitation, and these colors show the value of stresses. So in our case, we will apply this finite element modeling technique to our buildings and structures. So our elements may not look like this. Our elements will be representing beams, columns, slabs, shear walls and foundations, etc. So we will be modeling civil engineering structures using this technique. The overall finite element process may comprise of all of these steps, these ones. I'll explain them one by one. Don't know the reference of this picture, but that's something close to what you will be doing in this finite element analysis. So the very first step in this overall process is to prepare a finite element model, this one, and that basically comprises of discretizing or meshing the structure which you are going to model. You will be prescribing different loads which are applied to that structure, and you will also be prescribing or defining the supports or the boundary conditions on your structure. So modeling the actual structure geometry, prescribing load, and applying the support conditions or boundary conditions, all of these things basically are part of preparing the finite element model. Once the model is complete, there are different softwares which are available to solve that model. So the calculation part mostly will be performed by different software. Software will basically generate the stiffness matrix small k for each of the element, and then as the elements are connected to form an assembly, it will also assemble all small k's into a big global structural stiffness matrix capital K. It will also assemble all the loads into a load vector capital F, and it will impose the boundary conditions or the support conditions which you provided in the model. And if it is a linear static analysis, it will solve the equation F is equal to KU, and it will calculate the displacements, this U vector. So the development of this K matrix and the development of this F vector, these are the two basic mathematical steps in the finite element analysis. And once the software calculates this U vector by taking inverse of the K matrix and multiplying it with the F vector, once it calculates this U vector, it will use this U vector to calculate the local displacements, strains and stresses in the elements, and the local forces also. This process is sometimes called post-processing. It is also sometimes referred to as the stress recovery. So this is the overall finite element process, and if we decompose it to different tasks which we have to do, this will be these tasks. And not all the tasks will be accomplished or carried out by engineer. Let's see what are some of those tasks which the engineer is required to accomplish, and what are those things which the software will help in calculating. So the first step is to evaluate the real structure and convert it into a structural model. So you have to idealize your real structure and you have to convert it into a structural model. Both of these tasks require to be done by engineer. Both of these tasks. A finite element software will not help in these two tasks. But then the next step is to discretize that model into finite elements, this one. The finite element software will partially help in this task, but there will be some input required from engineer side also. So I write here as engineer also plus some help from the software also. The next step is to solve this finite element model, this one. If it is a linear static analysis, then equation will be F is equal to KU. That part will be completely done by software itself. In that part nowadays there is no input required from engineer. Then after you solve that, you will get some finite element analysis results. So then there will be a step about interpreting these finite element results, and that interpretation basically software will also provide some help in that interpretation by providing you some graphical displays of the results and some useful animations, etc. But engineer's input is the primary thing which is required in interpreting the finite element results. And last step is the physical significance of results. That realization or design decision making or any decision making basically should be completely done by engineer itself. So this is the overall scheme of work which is going to be implemented in the finite element analysis process. It starts with the idealization of the structure and it ends with the useful design decision making or realizing the physical significance of the results obtained from the analysis procedure. Let's now discuss about the very first step of this whole process, which is structural idealization. And let's say we have a three-dimensional continuum model here. This one is a three-dimensional continuum model, and that is governed by partial differential equations. The very first step of simplification can be geometric simplification, where we idealize this three-dimensional solid into a continuous model of a structure, but that continuous model is also governed by either partial or ordinary differential equations. That continuous model will have infinite degrees of freedoms, and we have not fix the location of degrees of freedom. So therefore basically each point on this continuous model is having degrees of freedom, and there are infinite points on this continuous model, so therefore there will be infinite degrees of freedom. The next step of simplification can be this idea of discretization, which we basically use in finite element modeling. So what we do in that simplification is that we will have some nodes in the structure, and the degrees of freedom can be defined only on those nodes, and those nodes will be connected by simple finite elements. These elements, this one for example, this one or this one or this one, these are finite elements connected by nodes, and degrees of freedom are only allowed at the nodes. So for example, here at this node we have 3 degrees of freedom, 2 translations and 1 rotation, this one. So this is called a discrete model of a structure. Contrast to the continuous model of a structure, this discrete model is governed by algebraic equations, and this can be solved by F is equal to Ku. We can construct the global stiffness matrix of this structure, and we can apply any forces on its nodes, and we will get the resulting displacement at nodes. You should note that these displacements will only be associated with the number of degrees of freedom, and the unknown displacements at each degree of freedom will be calculated. So that's how we can convert a 3-dimensional continuum model, this one, into a discrete model of a structure, and this discrete model will have finite number of degrees of freedom, So now for example, in this structure, if each node will have 3 degrees of freedom, so now there are 1, 2, 3, 4, 5, 6 and 7, 8. So there are 8 nodes, so there should be 24 degrees of freedom in this discrete model of our structure. But this continuous model will have infinite degrees of freedom. So the difference between a continuum and a structure is that a continuum extends in all directions and has infinite particles with continuous variation of material properties, deformation characteristics and the stress states. So all of these things, the displacements, deformation and the stresses, they vary continuously in a continuum. But instead a structure is of finite size, and it is made of an assemblage of substructures, components and members. So a structure will have finite degrees of freedom, it is of finite size, it will have finite number of displacements defined at its what we call as nodes. So structures can be categorized in many ways. For example, for modeling and analysis purpose, the overall physical behavior can be used as the basis of characterization, and we will have in this characterization different types of structures. For example, cable or tension structures, the structures which can only resist tension. For example, if you have a swing like this, so these 2 cables will only resist tensile forces. And then we can also have skeletal or frame kind of structures. For example, these kind of structures which are made from skeletal elements or frame elements. And then we can have also surface or spatial structures which are made of, for example, 2-dimensional elements, these kind of structures. Then we also can have solid structures. For example, foundations are solid like this, or pile caps, for example. Mixed structures which are comprised of 1-dimensional or 2-dimensional or 3-dimensional elements. For example, if you can have a slab which is supported by skeletal elements, beams or columns, then it is a mixed kind of structure that you have a skeletal element as well as the surface or spatial element. So there are different types of structures. Some of them you can see here graphically. This is a spherical dome, which is a basically a spatial element or 2-dimensional element. Then plane trusses or plane frames, for example, these are skeletal or bar elements or what we call as frame elements. This is, for example, a real building, beam slab building. You can see here that slabs are modeled with two-dimensional elements, and then the supporting frame is modeled with frame elements. So this is a mix of one-dimensional plus two-dimensional elements. Shells are two-dimensional elements. Storage structures, for example, here you can see, and some other kind of structures. So we can have cable structures, bar structures or skeletal structures which are made from one-dimensional elements, trusses or frames or grids, for example. We can have surface structures which are plates, shells or plane stress elements, and then we can also have three-dimensional solid structures. For example, here you can see this is a solid structure, three-dimensional element. For example, body of an arch or the body of a dam, for example, will be a solid structure. This is the dimensional hierarchy of structural members, as we also mentioned in the last slide. For example, we have a continuum. We can idealize it as a regular solid structure which have all the three dimensions comparable to each other, x, y and z. And we can also have an idealized plate or shell element which is a two-dimensional element in which two of the dimensions x and z, for example, are comparable, but the third dimension, which is the thickness, is far less than the other two dimensions. In one-dimensional elements, we have one length or one dimension far more than the other two dimensions. So if we have h and b as the cross-sectional dimensions of an element, then the length should be far more than both h and b in order to be classified as a one-dimensional beam element or skeletal element. So now we shift from classical solution, which is governed by the partial differential equations, to finite element solution, which is simple algebraic equation, which is f is equal to ku. So a real structure will have some governing equation of motions which will be in the form of partial differential equations. For example, this is the equilibrium equation for a real structure, and it is in the form of partial differential equations. With the help of some of the assumptions and the equilibrium equations and the stress strain laws, for example, the stress strain behavior of a concrete or a steel material, we also call them constitutive relationships, and with the help of compatibility and with the help of principle of virtual work, all of these concepts will help us in converting this classical solution of partial differential equations into a finite element solution, which is the solution of f is equal to ku. So our structural model will be governed by this equation, as the real structure was governed by this equation. Here we know already that the k is the stiffness matrix, u is the displacement vector, and f is equal to force vector. All of these components which will help us in exclusively converting this classical solution into FEM solution, they are discussed in detail in finite element analysis courses, and we will not go into detail of these topics. We will directly apply this method to our linear elastic model of a structure. We will model our civil engineering structure using finite element software, which will be ETABS in our case. But before going to that, let's see what is the stiffness matrix K made of. You remember the two-dimensional frame element which has 3 degrees of freedom on both ends. For example, this is one node and this is the other node, and we have 3 degrees of freedom 1, 2, 3, 4, 5 and 6 on both ends. At each node 2 translations and 1 rotation. So 1 and 2 is the translation and 3 is the rotation at this element, at this node. And similarly here 4 and 5 are the translations and 6 is the rotation at this node. So if you remember its local stiffness matrix, that was this one, and all of these entries are the stiffness coefficients of this stiffness matrix. So if you remember this matrix from the basic matrix structural analysis course, you can observe that this K matrix is basically a function of these 4 things: E, A, I and L. This E is the elastic modulus of the material from which this element is made of. So E is the material property. A and I are the properties of the cross section from which this beam element or frame element is made of. So for example, if this beam element is a rectangular cross section, this one, then this cross section will have a property A and I. So A is the cross sectional area, I is the second moment of area about centroidal axis. Then length of the member, this whole length, this one, length of the member, and that is the member property basically. This is not the property of material, it is not the property of the cross section shape of the element, it is the property of the whole beam. So it's a member property. So we can say now that this K matrix of a beam element is a function of material property and then cross sectional property and then the member property. This K is a function of the properties from these three things: material, cross section and then member. So now I will use this hierarchy of material, cross section and member to explain some of the important concepts of structural modeling in this lecture. So please keep remembering this idea that K matrix of any element is a function of material properties, is a function of cross section properties and then a function of member properties. So now we can answer this question: what is the stiffness matrix K made of? It is made of material property, it is made of cross section property and it is made of member property and then member property. The overall global stiffness of the structure K, capital K, is also comprised of the same three properties. Basically they are comprised of material stiffness, cross section stiffness and member stiffness. So we have the very starting point of the construction of K matrix, which is the material stiffness. That is defined as the resistance of the material itself to any strain. And that material stiffness manifests itself into what we call as the cross section stiffness, this one. And that is defined as the resistance of a cross section, for example rectangular cross section of a member or any cross section shape, for example this one, to overall strains. Now the cross section stiffness is not only made of the material stiffness, because that cross section will be made of some material, but the shape also will define basically the cross section stiffness, that shape. So material stiffness will play its role in cross section stiffness, but there will be an input from cross section geometry as well. So material stiffness along with the cross section shape or geometry will make the cross section stiffness. That cross section stiffness will manifest itself into the member stiffness, which is the next higher level. But the member stiffness will also be coming from the member geometry also, the length of the member, for example. That member stiffness is defined as the resistance of each member to its local actions. And that member stiffness from all the members in a structure will make what we call as the total structure stiffness, which is defined as the overall resistance of a structure to the overall loads. So this is the overall composition of this total K matrix. It starts with the material stiffness, for example E, elastic modulus of the material. It adds with the cross section geometry and makes what we call as the section stiffness, and then that section stiffness adds with the member geometry, for example length of the member and the overall configuration of different connectivity among elements, and then we get the member stiffness, and those members basically combined with the overall configuration of the structure or the structure geometry makes the structure stiffness. So the summary is that overall stiffness of the structure is derived from the overall geometry and connectivity of the members, their stiffnesses and the boundary conditions. The member stiffness is derived from the cross section stiffness and the member geometry. The cross section stiffness is derived from material stiffness and the cross section geometry. All of these stiffness relationships may be linear or non-linear, which means that they can follow the linear Hooke's law or they may not be following that Hooke's law depending upon the type of material or the type of structure. So the actual stiffness estimation, actual K matrix, can be influenced by the state of a structure at given time, can be influenced by these further factors, which is, for example, the damage in a structure or the level of deformation, the cracking or creep or shrinkage, or the level of stresses which are already induced in a structure. So all of these factors influence this K global also, apart from this typical composition. In all of these four levels, material, section, member, and then structure level, the relationship between actions and deformation can be linear and can be non-linear also. For example, let's say the material stiffness. If you are only defining the material with one number, which is the elastic modulus, then you are defining the default stress-strain relationship between a material which is forever linear like this. So basically you are saying that stress will always be equal to the elastic modulus times strain. So if you want to convert strain into stress, you will always use this expression. So it means that elastic modulus alone represents the linear part of the material stiffness. But the material stiffness can be non-linear also. For example, if you define the actual non-linear stress strain curve of a material, which may look like this, then that stiffness is the non-linear stiffness or inelastic stiffness, this one. So similarly, at cross-section level also, at member level also, and at structure level also, the relationship between actions and corresponding deformations can be non-linear also. For example, at cross-section level, the relationship between moment and the curvature of the cross-section, phi for example, can be non-linear. At member level, the relationship between moment and the rotation of the member, theta, can be non-linear. And if we make any of these material, cross-section or member level as non-linear, that non-linearity will automatically manifest itself at the structure stiffness level. So the overall structure in case of a non-linear material or a non-linear cross-section or member behavior will not follow F is equal to Ku. So F will not be equal to Ku for such a structure where any of the above elements or levels will have non-linear stiffness in them. So we will have a separate lecture on non-linear modeling of a structure, but for this lecture we will not discuss this non-linear modeling. So we will only discuss a structure which will follow F is equal to Ku in this lecture. But you should keep in mind that at any level we can make a structure non-linear. We can make a structure non-linear at material level or a cross-section level or at member level. So here in this slide I will show you what are some of the things which we have to provide to a finite element software in order to perform the finite element modeling and analysis for our civil engineering structures. So for all of those four levels, material, cross-section, member and structure, I will show you what are some of the properties which we have to provide to the finite element software. The very first step is the material stiffness. In order to provide material stiffness to the finite element engine, we have to do what we call as material modeling or material definition in any finite element software. If our material is elastic, which will be in this lecture's case, we have to provide at least these four properties, which is the elastic modulus, Poisson ratio, shear modulus and the coefficient of thermal expansion as the main input properties of an elastic material. And if we are performing nonlinear modeling, we have to define an inelastic material, and for that purpose we have to give the complete stress strain curve and the hysteretic model need to be defined. Hysteretic model. Hysteretic model is a rule which tells the software that how the material should unload, what stiffness it should have while unloading and what stiffness it should have while again reloading. So it's a rule to define the unloading and reloading path of the stress strain curve. So all those boxes which are green in color we have to provide to the finite element software. The second step would be the cross-section shape or cross-section geometry, and if we are performing the linear elastic analysis, we have to define an elastic cross-section of all of the elements which we are going to use in our structure, and some of the properties which will be required will be cross-sectional area, second moment of area, shear areas, for example. But in latest finite element software, we just have to define the cross-sectional dimensions, and all of the cross-sectional properties are basically determined from the initial dimensions which we provide to the software. If we are modeling the inelastic cross sections in a software, which we will be doing when we will be performing the inelastic or nonlinear modeling of our structure, in that case we have to provide the complete moment curvature curve and the hysteretic behavior of that curve, which is again a relationship between moment and the cross-sectional curvature, which will be basically nonlinear. And we also have to define the rule, which is the hysteretic behavior to unload, and what stiffness it should follow when reload, for example. So we have to define this complete cyclic behavior or hysteretic behavior for the moment curvature relationship. The third step is the member geometry, which is the member definition in a finite element software. If we are modeling the elastic members, only the lengths and orientations are required. In several latest finite element software, user can just simply draw these members. So you will be given a canvas in which you can just draw those elements like any drafting software, and then software will automatically know the length of those members for elastic modeling. For inelastic members, the complete moment rotation curve and the corresponding hysteretic behavior is required. So if we are modeling the members as inelastic members, in that case we have to provide this moment versus rotation of the member curve, the complete nonlinear curve, and the unloading and reloading path also, which is the hysteretic behavior. The last step would be this overall structural geometry. As we know that in several finite element software, we can simply draw the whole structure. We can draw all the members, we can draw the, for example, boundary conditions, we can directly define the applied loading also. So the overall structural layout, the global geometry and orientations are required in case of an elastic structure. For inelastic structure, obviously you don't have to provide any input directly at a structure level. If there is any inelastic material or inelastic cross section or inelastic member in your structure, that nonlinearity or inelasticity will manifest itself at the overall structure level. So this is the overall hierarchy which we will be following while we will be modeling our structure in a finite element software. We will start with material stiffness, this one. We then go to cross section geometry, all the cross sections of members which we will be using in our model, and then we will define all the elements, members basically, and then the assembly of those elements basically will make the overall structure geometry. So let's expand each of the steps again one by one and include the definition of forces and running the analysis also. So in this slide I will show all these steps one by one, and then we will follow those steps throughout this whole lecture. So I will be separating those tasks in this overall process in which the finite element software doesn't help, and then some inputs which we have to provide to the finite element software, and into those tasks which finite element software does for us. So the very first step is the structural idealization, in which we will conceive our structure, our model of the structure, and then we will start the finite element modeling based on that idealization. The second step is the discretization, that we divide our structure into elements, and in both of these tasks finite element software doesn't help us. We have to idealize our structure on our own, and this discretization although will be performed in the finite element software, but the initial thought or the initial idea by which the structure should be discretized should come from the engineer itself. Then there will be a set of tasks which we have to provide to the finite element software, and those tasks, as we saw in the last slide also, defining materials, defining cross sections, defining members, and connecting all those members into an overall configuration to make a complete structure. Then we have to apply loads. That also will be in green box, which means that this is a task which we have to provide to the finite element software, and then run that model. That means solve f is equal to ku if it is the linear static analysis, or this complete dynamic equation of motion if it is a linear dynamic analysis. And then post processing, which means the calculation of local forces, local displacements, element actions and corresponding deformations. Both of these tasks number 6 and 7 will be performed directly by software. And nowadays the finite element software also offer this facility to perform the structural design also. For example, ETABS provide this facility. So this structural design task will also be done by some of the finite element softwares nowadays. So our task is basically from -1, which means the structural idealization, up to the level 5, which is the application of loads. Obviously there should be one more step in between, and that is the application of boundary conditions. So let me write it here, maybe here, boundary conditions. So we have to define the restraints and supports in our structure. So boundary conditions should be there. So please keep this whole picture in mind throughout this lecture, and I will follow this slide again and again to explain some of the steps we will do in this linear elastic modeling of structures. So we will start with structural idealization, and then we will go through all of these steps one by one up to the step number 7. So a quick clarification between what I mean by members and by elements. A structure can be considered as an assemblage of physical components, and I am referring those physical components as members. So when I say the word members, I mean, for example, slab, beam, column, footing, for example. And in a finite element software, these physical members can be modeled by using one or more conceptual components, and I am using the word elements or finite elements for those conceptual components. So for example, one-dimensional elements, frame element, two-dimensional finite element or three-dimensional element. For example, plate element or shell element is a two-dimensional element in finite element formulation, and solid element is a three-dimensional element in finite element formulation. So there are conceptual components which are finite elements, and there are physical components which are members of a real structure. So most of the times there is directly one-to-one correspondence between them, physical components and conceptual components. For example, if you have a column, this column which is, let's say, fixed at both ends, this is a member, it's a physical component, but it can be represented by one frame element, this one for example, with two nodes, node 1 and then node 2, and the element is between these two nodes. So now there is a directly one-to-one correspondence between a physical component, which is a column, and a frame element, this one, frame element. So please note this difference among the members. This is a member and an element. So I will use the word element for finite elements and member for physical parts of a structure. The finite elements are a discretized representation of a continuous structure. Generally they correspond to the physical components, but sometimes dummy or idealized elements can also be used. So there can be some elements which maybe do not directly represent a physical component, but they can be included to include some special behavior in the model. For example, dummy beams sometimes used, or dummy frame elements are used to transfer loads from one element to another element. But that we will look into some next lecture, or when I directly perform the ETABS demonstration. Element behavior is completely defined within its boundaries, and it's not directly related to other elements. So for example, if you have a two-dimensional element, for example this one, with 4 nodes at its corners, when we define its local stiffness element, K local, in that element only the properties which are in between these elements, these 4 nodes, will be used to define this K local. So there will be no effect from another element. So one element is kind of stand alone in its mathematical formulation, and nodes will serve to provide connectivity across element boundaries. So there will be some other element also here, for example, and that element itself will have another k local which comprise of the material and cross section properties of this element itself, and it will not have any effect from the other element. So nodes are imaginary points which serve to provide connectivity across element boundaries. So here you see that we have a physical object. We discretize it into 3 finite elements with these nodes. So now this is a node, this is a node, this is also a node, and this node, for example, is a node which provides the connectivity between this element and this element. So it provides the connectivity between 2 finite elements. The finite element solver will calculate the displacements only at these nodes, not between the elements here, not here, but only at nodes. So this displacement will be converted to stresses and strains, and those stresses and strains will basically be interpolated to the elements and will be used for the purpose of structural design. So basic categories of finite elements, as I have discussed already, we have one-dimensional elements, we have two-dimensional elements, and we also have three-dimensional finite elements. They can also work in combination to represent a real structure. In one-dimensional elements, only one dimension is actually modeled as a line. The other 2 dimensions are represented only by stiffness properties. So for example, all the skeletal structures, one-dimensional or two-dimensional or three-dimensional models, they can make use of, for example, one-dimensional elements like this. So all the skeletal structures will be using one-dimensional finite elements. In two-dimensional elements, only 2 dimensions are actually modeled as a surface like this, and the third dimension, which is the thickness of these surface, is represented only by the stiffness property. And using these 2D elements, we can model a 2-dimensional or also a 3-dimensional model also. For example, you can have 4 walls all modeled with a 2-dimensional element. Now it will become a 3-dimensional structure modeled with 2-dimensional elements. And we also have 3-dimensional elements in which all the 3 dimensions are modeled as solid. So for example, if you have a 3-dimensional structure, for example a pile cap or a thick raft foundation, that will be required to be modeled as solid object, and that solid object can be modeled using 3-dimensional solid elements. In reality, all of the 3 types of these elements can be in one model to represent a real structure. In civil engineering structures, most of the times we only need 1-dimensional and 2-dimensional elements. For example, 1-dimensional element can represent our beams and columns and struts, and 2-dimensional element can represent our shear walls, slabs, and for example masonry infill panels and other 2-dimensional elements. There is one more classification of structural modeling which we call as macro modeling and micro modeling. Macro modeling is the modeling of the whole structure itself. For example, here you can see is a finite element model of a storage structure, and in this kind of a model the objective is to get the overall structural response. If we create a model of a complete building for the purpose of getting overall structural response, that will be called as a macro model. The results will be in the form of member forces and the stress patterns, for example, member displacements also you can see. Global modeling or macro modeling is same for nearly all materials, and material distinction is made by using specific material properties. And this kind of a global model may be a simple 2-dimensional beam frame model or a sophisticated 3-dimensional finite element model. So the global model means that we model the complete structure. We are interested in the overall global behavior of the structure. We are not focusing on a particular part of a structure, and this macro modeling is generally adequate for the design of usual structures. On the other hand, we have what we call as micro modeling. if we are interested in getting the response of a single element or a single member, so we can model that single member alone or part of that member, and then we can analyze that in more detail to get the response. For example, those single members can include the modeling of cross section, the modeling of openings in a slab and shear wall, for example, the modeling of joints between beams and columns, and some other connections, for example. The objective in this micro modeling is to determine the local stress concentrations, cross-sectional behavior, modeling of cracking, for example, the prediction of cracking, for example, the bond and anchorage studies. In all these cases, we will not model the complete structure itself, but we will model a part of that element only. For example, here in this model you can see it's a micro model of a mechanical assembly in which we need very fine mesh, and we also need the advanced element features. We may also go for nonlinear analysis if we want to go into that much detail. And this micro modeling is mostly suitable for research, simulation, experimental verification, and theoretical studies. In our civil engineering structures, if the purpose is structural design, we will mostly go for macro modeling. So there can be more than one possible ways of structural idealization also. For example, let's say we have this structure, a real structure, which is comprised of a slab with supporting frame elements, this one. So the figure A is the real structure. One option to model this real structure is what we can call it as a solid model, that we use the solid three-dimensional elements. So all of these small elements are three-dimensional elements, and we use those elements to model the geometry of this whole structure. So all of these elements are, let's say, three-dimensional elements, finite elements. So that model will be called a solid model. Another option can be that we go for this 3D plate frame model, in which we model the beams and columns as frame elements. So these are frame, and this slab basically is modeled using two-dimensional plate elements. So this is plate, and the combination of these plate elements and frame elements make a 3D plate frame model. This is also one option to idealize this real structure. Another option can be that we ignore the slab here and we just model the skeleton of the structure using 3D frame elements only. So all of these elements, they are all frame, and we ignore the slab. Another simplification can be that we just create a two-dimensional frame model of this real structure for the purpose of analysis. So we just take one frame, for example, we cut the real structure from here and we only take out this frame, this one, and we idealize it as a two-dimensional frame element, a portal frame, for example. A further step of simplification can be that we make what we call it as a grid plate model, and that can be that we model the slab with plate elements and we don't explicitly model the frame elements which are supporting the slab. So now you can see that there is a decreasing level of sophistication in the model B to F. The model B is the most sophisticated model, and obviously it will take more time to run also, but that will capture the complete behavior of this real structure because it is based on less assumptions and it models almost the complete geometry of the structure. So B may be called as the most sophisticated model, This C can be called as a practical model, for example. So C is a practical model. It is not as sophisticated as option B, but it will capture almost all important aspects of the real structural behavior. So the supporting frame will be modeled using frame elements and the slab is modeled using plate element. If we are not interested in the behavior of plate or slab itself and mostly interested in the behavior of supporting frame, then option D will be useful for us. So D is a kind of one step lower than option C, is slightly less sophisticated because it is based on ignoring the slab behavior in the model. And if we further simplify our model and we are only interested in the two-dimensional behavior of frame elements like the bending of columns or sway of columns itself, then we can use a two-dimensional frame element, which is the option E here. And lastly, let's say if we are only interested in the behavior of slab and we are not interested in getting the behavior of the supporting frames, then we can go for this option F, which is based on the explicit modeling of slab only and excluding the frame from the model. So F can be used if we are interested in getting the behavior of slab only. So this example shows you that there can be different levels of modeling depending upon what behavior you are looking for or what kind of response you are mostly interested in. Starting from the most sophisticated model, which can be three-dimensional model, up to a simplified two-dimensional model in vertical plane or in horizontal plane, for example. So a quick guideline about the selection of elements for the purpose of structural modeling. You have to keep in mind that what is the basic issue which you are looking for in the structural behavior and why you are modeling that structure. So the need of modeling should be kept in mind while selecting the finite elements for the purpose of modeling. You also have to see how the materials are represented and modeled in a particular element, and you also have to keep in mind all the types and properties of various elements which are available to you. So in later part of this lecture, I will show you what are some of the elements which you can use in CSI ETABS or SAP, for example. And then you also have to select appropriate elements for representing different structural members. Obviously, you cannot use a one-dimensional element to represent a real structural member, which is, say, three-dimensional member or a two-dimensional member. So you have to select appropriate element. So you have to keep that dimensional hierarchy in mind also while selecting the elements. So number one, you should keep the need of modeling in mind. Need of modeling. Why you are modeling that structure. If you are modeling to get the global response, for example, then no need to model the complete structure with three-dimensional elements. The second thing is you should keep in mind the materials, how the materials are going to model. The third thing is that the element menu, what are those elements and what are their behaviors which should be available to you, and then they will help you in selecting the suitable elements for your purpose. And the last thing is the dimensional hierarchy, which you should keep in mind before the selection of these elements. So one important current modeling trend, and that is also implemented in CSI ETABS, which you should know now, is the object-based modeling. Object-based modeling. In several software, the graphic objects representing the structural members are automatically divided into finite elements. So nowadays, in modern finite element software, you don't need to define the element one by one. All you need to define is a graphic object, and the software itself will convert that graphic object into the finite element. This kind of modeling is called the object-based modeling, and it makes the finite element modeling of a structure very simple or very convenient for the users. This object-based modeling basically also involves features like, for example, auto meshing, auto load computation, and auto load transfer. So nowadays you don't have to worry about some of the finer details of a finite element model. All you need to do is to create graphic objects which will represent your structural members, and software will convert those graphic objects into a combination of finite elements for you. So there can be different levels of object-based modeling. The level 1 can be that nodes are defined first by coordinates, and then elements are defined that connect the nodes. This is level 1. This is mostly time consuming and it requires more effort. Level 2 can be that the elements are defined directly. For example, you directly define a column either numerically or graphically, and the nodes are created automatically. So if it is a column, you define directly, and the nodes, which is this one and this one, it is created automatically. The level 3 is that the structure is represented by generic objects and the elements and nodes are created automatically. For example, let's define a generic element as, for example, shear wall, and the software will ask you to directly draw a shear wall, this one, let's say for 5 stories. You directly draw or define this shear wall directly, and the software will automatically create those shell elements and the nodes which are required to model this shear wall. So for example, it will automatically mesh it in the shell elements and it will create these nodes, these ones for example, at each story level, which will be connecting these shell elements. Similar is true, let's say, for slabs, that you define a generic object called slab, for example, and the software will automatically divide it into plate or shell elements and it will create all these nodes automatically itself. So this level 3 is the type of modeling which we will be doing in ETABS, and in which we will directly define the generic objects, shear walls, beams, columns, slabs for example, footings for example, and the software automatically will create finite elements and the nodes required to connect those finite elements automatically. So now you are familiarized with another terminology, which is objects. It is different from finite elements, and that terminology is specific only to SAP 2000 or ETABS. So the physical structural members in a structural model will be represented by objects in ETABS. So when I say, for example, a slab object or a shear wall object, you should know that it is not a finite element, it is a physical structural member, and it will be automatically converted into finite element or a combination of finite element and nodes when the analysis will be run. So using the graphical user interface, you directly draw the geometry of an object and then assign properties and loads to the object, not to the element but to the object, to completely define the model of the physical member. So whatever properties you will assign to that object or whatever load you will assign to that object, that will be converted into finite elements and will be automatically transferred to those finite elements. So for the analysis purpose, SAP 2000 will convert each object into one or more finite elements and develop an analysis model. That analysis model will be created at the back end when you will run your object-based model. So what are some of the objects available in ETABS or SAP 2000? The very first type of objects is the point objects, or we can call it, for example, zero-dimensional objects, and they are of two types. One is the joint objects, which are automatically created at the corners or end of all the other type of objects. So for example, if I create a slab object, so it will automatically create 4 nodes or point objects basically at the 4 corners of this slab object. And also they can be explicitly defined at a certain location in the model to represent supports. For example, if this is, for example, a column, this joint object can be assigned some property which is the support, for example, or to capture any local behavior also. The other kind of point object is the grounded one joint link or support objects. These are also used to model special member behaviors in the model. We will discuss it in more detail when we will discuss the point objects in ETABS. Line objects in ETABS is of 4 types. The very first common type is the frame object. It is used to model, for example, beams, columns, braces, and truss elements. The other kind of line object is cable objects, which can be used to model only tension taking elements. Tendon objects used to represent tendons within other objects, mostly pre-stressed elements, and the connecting two joint link or support objects, and they are also used to model special member behaviors just like one joint link or support objects. The next type of objects is the area objects, and those objects can be converted into either shell elements, and in shell we again have three types. One is the plate behavior, another is the membrane behavior, and then their combination, which is called the full shell behavior, and we will see in more detail in next slides about them. But these are all the area objects in ETABS, and they are used to model walls, floors and other thin walled members in a structure. And then we also have solid objects. They are only available in SAP 2000, not available in ETABS, and they are used to model three-dimensional solids, for example pile caps or thick raft or foundations. So when you run an analysis in ETABS or SAP, the software automatically converts your object-based model into an element-based model, and that element-based model is called the analysis model. It is the finite element model, and it consists of the traditional finite elements and joints. You cannot see that model, you can only see this object-based model on your screen. The results of the analysis model are reported back to the object-based model, and you can see all those results on your object-based model. There is another terminology which you should know, and that is group. A group is a named collection of objects that you define. So you can define different objects into one group, and you can give it some unique name, and this kind of groups are mostly required by some special kinds of analysis. For example, one of the analysis type which requires the definition of these groups is the construction sequence analysis. Construction sequence analysis. In this analysis, you define different parts of your structure in groups, and the software can apply the gravity load in different steps based on the groups you define. So using this option, you can actually mimic the sequence of the application of gravity load as followed in the real construction case. So that's all about structural idealization. The next part will be the structural discretization and the element menu, which means what are some of those elements which will be used to discretize your structure to make a finite element model. So we will discuss this in next part of this lecture. Till then, take care and stay safe. See you in the next video.